All right, hello, that's a little loud. Hello, everybody. Hope your weekend was good. Your exam is currently open, available at the testing center. Closes tomorrow. Be aware of that late fee, which they mandate and kicks in at 2 p.m. It's historically a way they've learned to manage crowds at the testing center, because they speculate that about half of you will choose not to pay the $5 fee and take it earlier. I'm not sure how well that bet works out statistically over the past, but that's sort of why they're doing that. I wanted to say one thing. There's a problem on the problem set that many of you have emailed me about. I forget what the specific context was. It was one of these electrophilic aromatic substitution reactions. It was supposed to be Friedel-Crafts, and the key that I wrote, it looks like I was trying to write CH3, and I stopped after writing the C in one line of the H, so it looked like there was magically a chlorine there. If you know what I'm talking about and we're worried about it, don't be. Those should be the Friedel-Crafts alkylation product. I don't know. Nobody's blank stare, so okay, I guess nobody noticed. It's fine. Okay. We are beginning chapter 22 on amines. Some of this today is going to be some review, which I think will be good because some of you are stressed out about the exam and you don't want to learn anything new today. There will be a few new things, and we'll also tell you the story of how a failed chemical reaction made an 18-year-old British kid extremely wealthy, as we talk about the birth of the modern chemical dye industry. But to begin with, amines are molecules with nitrogens in them in general. And though they can vary a lot in context, you're of course used to the idea of a primary amine versus a secondary amine versus a tertiary amine. Amines are both nucleophiles and bases. The conjugate acid of amines are ammonium ions, and you're used to thinking of ammonium ions from your pKa table as having pKa's that are in the range of around 11, and so at physiological pH, amines are often protonated. More on that later. But we've learned to talk a little bit, to use some of our intuition about resonance and aromaticity to sort of rank amines in terms of their basicity. And this is a useful skill, and actually talking about it now will be one way that you can review some of the things that we learned in chapters 19 and 20 about aromaticity. So let's begin there, and let's do a few various comparisons. Let's sort of ask the question, a molecule like this that I've drawn above would be called ethylamine, and it is an example of something that's called an alkylamine. And let's compare the basicity of the alkylamine with something that we're going to call an arylamine. This is, in this case, the molecule aniline, which is an example of an arylamine. An arylamine is one where one of the groups attached to the nitrogen is an aromatic group. So the question that we want to ask is, which is the stronger base? And there's multiple ways you can rank bases. You can consider the stability of the lone pair on the nitrogen. That's the place of the molecule that's basic. You can also consider the stability of the conjugate acid and think through it that way. In this case, it's going to be most productive for us to think about the stability of the lone pair that's basic. So what have you got? What reasons do you have to suspect And remember, more basic means a less stable lone pair. So any reasons to suspect one versus the other of these as being more or less basic? Go ahead.
The one on the benzene would be less basic because it's conjugated.
Okay. Less basic because you said conjugated, so that means you mean that the lone pair is resonance stabilized, right? Presumably, we won't draw those resonance structures, but you could draw a resonance structure where this lone pair would form a pi bond between the nitrogen and the carbon, and that would put partial negative charge on carbons 2, 4, and 6, right? That's clear to you because you've long since gotten used to thinking of anilines, or those nitrogens, those NH2 groups, as being electron donating groups, right? Which means they're donating away from where they are. That should make them less available to act as bases, okay? How about this? Among arylamines, are there ways that we can reason our way through some examples? So let's compare aniline again versus arylamines where we put other things on the benzene ring. So what about para-nitroaniline? And what about para-methyl-aniline? Let's see if we can rank those in terms of basicity. Remember, the principle is we've said that aniline is a weaker base than the alkylamine, a stronger base, because the lone pairs in aniline are stabilized by resonance. So what do you think the effect of an electron withdrawing group versus an electron donating group is for the lone pairs on these aniline derivatives? What do you think? Nitro, more or less? Less basic? Okay, that is the right answer, but you had a 50-50 shot. So let's see if you know the answer better than just random. Why? Go ahead.
Because the nitro group is electron withdrawing, which makes the benzene then electron poor, so now that pulls the
Right.
electrons further.
Right. That's the reasoning is that the nitro is an electron withdrawing group via resonance. That makes the benzene ring electron poor, which encourages donation of the lone pair on the aniline into the benzene ring. The key resonance structure, which I will draw, is this one, in which the lone pairs in the aniline are now in the pi bond with the benzene ring, and then we move electrons from the benzene ring out onto the nitro group. This is the resonance structure. You can find this in your text in sample problem 22.3 if you're a little bit confused, and they'll give you a little bit more detail on how to get that resonance structure. By the same token then, you would expect an electron donating group to make the benzene ring more electron rich, and that would decrease the extent to which the aniline lone pair is able to donate in the ring. And so the aniline lone pair in the para-methyl should be more basic than aniline, okay? So you're seeing how we can use these basic principles that we've learned so far to rank molecules in terms of basicity. What about the impact of, let's now compare an alkylamine with an alkylamide. Which do you predict is more basic, the amide or the amine? Got a 50-50 shot, so yeah.
The one on the right.
Okay. The amide is, you're saying, is more basic or less basic?
Less
Okay, you are right. Why is that?
It's because you've got a carbonyl carbon, so it's electron poor, and so it's going to want to have, there's a resonance structure there.
Good. Yeah, you have a resonance structure where you donate the amide nitrogen lone pair to form a new carbon-nitrogen pi bond, and you move the pi bond from the carbon-oxygen pi bond out onto the nitrogen to get this resonance structure. Same basic idea. Resonance stabilizes the lone pair and makes the lone pair less basic. So amides are not good bases at all, which is why I've never, ever, ever shown you the pKa for this because it's really, really low. Okay, and so low that I'm going to actually erase it. We're never going to think about it again. So yes, resonance stabilization makes the amide less basic. Okay. Incidentally, this is maybe a good point, a good time to review something, and actually answer a question that was given before class. We said in chapter 20 that the reactivity of the lone pairs on aniline is a problem in Friedel-Crafts reactions because the lone pairs act as a Lewis base to attack the aluminum chloride catalyst in a Friedel-Crafts reaction. One of the workarounds that you probably encountered in your text is, and in doing some practice problems, is to make an amide out of the aniline. Okay, so this is the amide version of aniline, and there's a particular problem on your problem set where you go on to do, and I don't remember exactly what it is, a Friedel-Crafts reaction on that starting material, and whereas if you didn't have the amide there, the lone pairs are too reactive and interfere with the Friedel-Crafts reaction. If you do have the amide there, the reaction proceeds normally as expected to give you the expected mixture of ortho and para products. Why do you suppose it works for the amide but not for the aniline? What's going on there? Go ahead, Maria.
It's not basic enough to attack the intercalary.
Yep. Right. The amide version, the lone pair, is not basic enough to attack the aluminum chloride and interfere with the catalysis. Now, a related question is, why do we see ortho and para substitution here? And there was some confusion over whether this amide is indeed an electron donating group versus a withdrawing group. You do see ortho and para substitution. Why is that aniline still a donating group? Still got the option to do this, right? And put electron density into the ring. Is the amide a better or worse donating group than just the regular aniline? Worse. So it's not as good. This is a better electron donating group via resonance. This is a slightly worse. Worse is going to drive some of you to worry, so I'm going to say not as good electron donating group via resonance. It's not as good as the aniline because of the impact of that carbonyl. Why is this not a withdrawing group? Because you don't have a pi bond between the nitrogen adjacent to the ring and something that's electronegative. There's no way to draw a resonance structure where you push electrons out of the ring onto that nitrogen. Okay? Kenny, did that answer your question, sort of? Follow-up question? No? Okay. All right, good. All right, there are other ways that you can compare basicities of nitrogen-containing compounds. And to do this, we can compare sometimes nitrogens within the same compound. We've done this problem before, so frankly, you should be able to get it without a lot of trouble here. You have two nitrogens in this molecule. This is imidazole, which is most basic? Which lone pair is most reactive? Go ahead.
The lone pair in the sp2 orbital because then it's able to interact with other things to get things.
Okay, lone pair in the sp2 orbital. We've said before, what kind of atomic orbital holds that lone pair? P orbital. All right, be careful here. You're right. I thought p orbitals were higher in energy than sp2 orbitals, so why isn't that lone pair more reactive? Yeah, Matt.
If you had an sp2 bonding orbital, that would be lower energy. But, or if you had an sp2 that was participating in the bonding orbital, but lone pairs are at the break-even line.
Lone pairs are at the break-even line, though you can rank them in terms of orbital hybridization, and a p atomic orbital is higher in energy than an sp2 orbital. But is that lone pair really in a p atomic orbital? Go ahead.
Well, I think those lone pairs are helping like maintain aromaticity,
There you go.
and so
Frost
they're not-
circle.
Yeah, they're not going to be used in a reaction when the other lone pairs could and keep aromaticity.
Excellent, right. So actually, the lone pairs on that nitrogen are not. It's fine to think of them as being originally held in an atomic p orbital, but actually, they are part of an aromatic pi system, right? And so the lone pairs that I've highlighted in blue there are involved in aromaticity, which automatically moves them lower in energy than our sort of break-even non-bonding line. So the most reactive lone pairs are the lone pair on the in an sp2 orbital on the pi bonded nitrogen. That's a multi-layered argument. If you just memorize one fact, you're going to get it wrong. Okay? The lone pairs in the sp2 orbital that are orthogonal to the pi system are the most basic lone pairs in that molecule. The other lone pair is actually in a bonding orbital that's involved in aromaticity. Okay? The other way you can reason your way through this is to consider the conjugate acid. In the chemistry version of the Sermon on the Mount, when Jesus says, "Consider the lilies of the field," what he really says is, "Consider the conjugate acid." And so let's draw the two conjugate acids. If we draw the conjugate acid where the lone pair, not really, okay, I'm end of semester. Dr. Price was completely sacrilegious when he said, "Consider the." Okay. Anyway, let's draw the conjugate acid for if we put a lone pair on this nitrogen, the sp2 nitrogen with the lone pair. Now let's consider the other conjugate acid where instead we protonate the other nitrogen. That's going to look like this. This one is better. This one is worse. Tell me why. This one, what's wrong with this one? Is it anti-aromatic? It's just simply not fully conjugated anymore. It's simply not aromatic because not fully conjugated. The other nitrogen, the one that we protonated, is now sp3 hybridized. The ring is no longer fully conjugated, but the one on the left is still cruising around with aromaticity. It's still happy. Okay? And you can do this all the time, thinking about nitrogens in various rings. Let's use now another comparison. This is a base that is called piperidine, This is a base that is called pyridine, and it's spelled with a Y. Both of them stink to high heaven. A lot of amino compounds are smelly. We'll talk about actually that in a little bit. But they differ in basicity, and you can compare them by considering the hybridization of the two lone pairs. In the one on the left, sp3 hybridized, and the one on the right, sp2 hybridized. Now, we're going to rely on hybridization when everything else is equal, right? Neither of those lone pairs is involved in an aromatic pi system. You can tell that that's not the case here because there is no aromaticity. Over here, we've already got our aromatic system present in the double bonds, and the lone pairs in an sp2 orbital. So in comparing these two, we can just fully go with the hybridization of the lone pair. Based on what you know about orbital hybridization, which of these is lower in energy, the sp3 or the sp2? sp2 is lower in energy. It's got 33% s character, and the s orbitals are lower in energy than p orbitals. So orbitals with greater s character are lower in energy than those with less s character. So you would expect pyridine to be a weaker base, lower in energy. The lone pair should be lower in energy than in piperidine. And indeed, piperidine is more basic. Okay, questions you want to ask? And it turns out that difference is actually reflected in the pKa's of the conjugate acid. If you look up the pKa for pyridine, the conjugate acid, it's 5.3. If you look up the pKa for the conjugate acid of piperidine, that pKa is about what you would expect for a normal alkylamine. And so hybridization can make a big difference. Asking which of these nitrogens is more basic is the exact same question as asking which of these acids is more acidic. Yeah?
Just looking at the conjugate acids, it seems as if the positive charge on that nitrogen would be able to across the benzene.
Is it possible to delocalize that positive charge on the pyridine by resonance?
For the nitrogen.
On the nitrogen, the answer is no. You could go to the other resonance structure of the ring, but the nitrogen would still have a positive charge. So does resonance help there? Probably not. It's probably purely a hybridization effect. Okay, other questions? Okay, good. So now we want to actually do a couple of things. I want to tell you about some interesting amine compounds. I always hesitate to do this because somebody's going to ask, so is this going to be on the test? And the answer is, if you ask questions like that, then it will be. No, ideally when we talk about molecules and that are interesting, it's because I think some of you may be prescribing these molecules in your future, and it's my job to show you the structure because I'm not sure anybody else ever will. And if you're going to prescribe a molecule and put it into a human and expect it to do something, you should probably have some vague idea of what the atoms you're prescribing are. The standard for what should I know for the test is you want it to appear that you were in class and listening. So memorizing structure is generally not that useful. Being able to rationalize results and explain them sensibly is usually much more useful. So there's a ton of different molecules that have nitrogens in them that are pretty interesting. Some of them we'll talk about are interesting from a medicinal point of view. So we're going to talk about adrenaline or epinephrine and norepinephrine and related molecules which include methamphetamine, and I think ecstasy, and then some others. So what I'm drawing for you now is adrenaline. Which is a hormone secreted in response to stress. It can also be administered, and I'm not sure because I'm not a physician, but every time I watch The Good Doctor and somebody's coding, they sometimes inject epinephrine to do something with the heart. So good luck figuring out what that is on your medical tests. Adrenaline has this core structure. It's called 2-phenylethylamine. Here's the ethylamine portion, and here's carbon 1, and here's carbon 2. And so you can see that the phenyl group is on carbon 2 relative to the nitrogen. So all of these molecules are derivatives of 2-phenylethylamine. Noradrenaline is just, so this is adrenaline, or epinephrine is the alternative name. Noradrenaline is a neurotransmitter rather than a hormone, and it increases heart rate and dilates air passages. So this is noradrenaline, and it just lacks the methyl group, which makes a big difference in terms of its effects. You can see when I draw methamphetamine, the same basic structure. You've got the 2-phenylethylamine kind of structure. Oops, that's too close. There's another carbon there. There's the nitrogen, there's the methyl group. And methamphetamine has a methyl group. That's where the meth in methamphetamine comes from. And is a stimulant, but it has that same core structure, the 2-phenylethylamine. And then there are some other amine molecules that sort of share this same, share this sort of structure. So, those are the ones we wanted to talk about. So you'll hear people talk about these, but they all have the same sort of structure and the same basicity. In all cases, those nitrogens are not conjugated. I want to talk now about some neurotransmitters and amine-based drugs that actually inhibit or promote various concentrations of neurotransmitters. You've seen, I'm going to get that wrong. There we go. So the neurotransmitter dopamine, which you hear about a lot, actually shares some structural elements with adrenaline. It's got the same 2-phenylethylamine structure, and like adrenaline, it's got the benzene ring with the 2 OH groups on it. What's missing relative to adrenaline is you've got this hydroxy group and then the methyl group on the nitrogen. Dopamine's a neurotransmitter, meaning it's involved in cell signaling between neurons, and it's related to processes that control movement and emotion, so it's really important for health. And you'll hear people talk about it as a feel-good chemical. A related neurotransmitter that's similar in structure, though the aromatic ring is entirely different. It's got a benzene ring and then a 5-membered ring attached to it. Dopamine is actually derived from the amino acid L-dopa, which you can get from tyrosine. Serotonin is derived from the amino acid tryptophan, and it's got this aromatic ring with a nitrogen in it. This type of aromatic ring is called an indole, and this is serotonin, and is involved in mood and sleep, perception, temperature regulation. And it's thought that serotonin levels can be off in some cases relating to depression. And so this has led to the development of a class of drugs called SSRIs, which stands for selective serotonin reuptake inhibitors. There's a receptor that binds serotonin and brings it back into the cell, back into the neuron, so that after a signal is gone, after a signal's been released, serotonin's been released as a neurotransmitter, you take it back up so the signal can go off. SSRIs inhibit that reuptake, which overall increases the amount of serotonin present in the space between your neurons, and that can tend to have antidepressant effects. So there are molecules that do this, and interestingly, they too are amines. Sometimes when you want to block a receptor, you invent a molecule that looks a lot like the thing that should normally bind that receptor, but differs in key aspects. Perhaps it fits even better. So I'll show you the structures for a few SSRIs. One of these is called fluoxetine or Prozac, and this has a benzene ring, and then attached to that is a carbon. So this is not a 2-phenylethylamine derivative. It's got an extra carbon between the nitrogen and the benzene ring. But you can see how it is an amine kind of like serotonin. And so you could imagine how it could maybe interfere with the receptor. That's marketed under the trade name Prozac. The other, which is pretty famous and which I've actually taken before, is called sertraline. And this is a little bit more complicated, but you'll see that it actually shares the same 2-phenylethylamine core structure. You've got a benzene ring fused to a cyclohexane with a nitrogen hanging off the front. And then over here, there's another benzene ring with 2 chloro groups. So a great multiple choice question for this portion of the class would be, which of the following is Zoloft? I'm just kidding. Man, lighten up. It's an exam day, so you can't lighten up. Notice the benzene ring and then, it's not exactly the same structure as a 2-phenylethylamine. So sertraline's interesting. As I said, I've taken it before for depression, and it has some interesting side effects that I noticed. So I'm just going to tell you this because some of you are going to prescribe this in the future and you need to know about it. One of them is really fascinating. It's called bruxism, which means grinding of your teeth. I noticed this within days after starting. It became difficult to chew my cereal in the morning. I'd be crunching on my, not Fruit Loops, because we buy Malto meal in our house, Tutti Fruttis. And I noticed my jaw getting tired and like, what's going on? So I looked it up, and in fact, yeah, it does cause you to clench your jaw quite a bit. Another weird side effect was a little bit of dizziness. I noticed, especially when moving my eyes, I'd get a little bit dizzy. And then here's an annoying one. What's it called? Insomnia a little bit. When you first start, I would wake up at like 2 in the morning and be wide awake and be like, and angry for a while. A lot of these things go away after a while. And in general, for me, the sertraline did sort of smooth out the highs and the lows. And anyway, it can be a very, very useful tool. Hopefully in today's world, the stigma for medication for mental health issues is going away. It still remains in certain quarters. Just encourage you to think about it as a useful tool in the toolbox. Kind of like if you want to get in shape, diet and exercise are good. If you need mental health help, sometimes therapy and medication are good tools in the toolbox. And as physicians, please do not make people feel bad for getting medications to help with their problems. Duh. Okay, so now we want to talk about some chemistry. We're going to talk about use of amines in synthesis and synthesizing amines. Oh, I forgot, this is important. When you go to prescribe sertraline, it will often be prescribed as the hydrochloride salt. Or if you're like me and you have a bottle of this at home, you'll see it says sertraline HCl. What's the HCl? Does that mean that the sertraline is floating in some concentrated sulfuric acid? And isn't that bad for you? No. It means that this is an amine, and sometimes amines are insoluble in organic solvent. I'm sorry, sometimes amines are not soluble in water, but they're bases, and if you add a little bit of HCl, you protonate the amine to make the ammonium chloride salt, and that is soluble in water, so that's absorbed much more easily. If you want another example of this that's involved in United States sort of drug enforcement policy, if you go look up the structure for cocaine, which I should have memorized, but I don't, cocaine is an amine. And it is, you can either, you can take it in the, what's called, let's see, sorry, I need to give you a few terms here. The regular amine, which is not protonated, is often called the free base. And then the other version where you protonate the nitrogen is called the hydrochloride salt. So free base and hydrochloride salt. I don't know, when I say free base, I think of the song Free Bird with its epic guitar solo, but I don't think that free bases are necessarily any more cool than than hydrochloride salts. I'm sorry, officer, the reason I was speeding is that I was listening to the Freebird solo. It's hydrochloride salt. I can't think and write at the same time. Happens to me a lot. Anyway, if you go look at the structure for cocaine, it is an amine. In its free base form, it is not soluble in water. In its hydrochloride salt, it is. In the free base form, it's kind of a sticky solid. In the hydrochloride salt, it's a fine white powder. That's the difference between crack, which is the free base, and then the powder cocaine, which is the hydrochloride salt. Incidentally, the free base, the penalty for taking crack was insanely higher than the penalty for possessing the hydrochloride salt. And you should read about that. It's an interesting story in drug policy and overlaying societal issues, including poverty and racism, with drug enforcement policy. And in some ways it makes no sense, right? That taking the free base should get much stiffer penalties than taking the hydrochloride salt. Anyway, so I'll leave that to you since this is not a political science course, but it's interesting to know some chemistry related to it. Now let's talk about amine synthesis. We're going to spend maybe 5 minutes on that, and then I want to tell you the story of the 18-year-old from the UK that got rich off a failed reaction. So one of the problems with making amine molecules is that primary amines are not as reactive as secondary amines, which are not as reactive as tertiary amines. Part of the reason for that is the alkyl groups are electron donating, and the more alkyl groups you have on an amino group, the more likely a reaction is to go to happen fast. So one of the classic problems in synthesizing amines via conventional SN2 reactions is you could say, okay, I want to add another ethyl group to make diethylamine, but then what you make, the secondary amine, is more reactive than the primary amine, and so you would go on to make multiply alkylated amines in sort of an uncontrolled over-alkylation process. So one solution to this is a pretty creative amine synthesis reaction called the Gabriel synthesis. And here's how it works. You take a starting material that has a nitrogen in it, but the nitrogen, the lone pairs on the nitrogen are pretty well tied up in resonance with electron withdrawing carbonyl groups. This amine-based compound has a strange name that involves a pH and a TH, and you just basically pronounce that as F and a TH. So mostly people drop the F and just call that phthalimide. Because I want to protect the people in the splash zone, I won't attempt to do the F and the TH together. Right, exactly. So the Gabriel synthesis starts out with phthalimide, And you can use hydroxide as a base to remove this proton on the nitrogen, which has a pKa of 10. The reason it's got a pKa of 10 is because the nitrogen is resonance stabilized. So you make the anion of thalamide, which is and then, so let's draw it like that. Then you use that as your nucleophile. But the idea is that only one alkyl group can be added. You can do the classic SN2 reaction there with an alkyl halide. Only one alkyl group can get added because the other lone pair is again involved in resonance with the two carbonyl groups. So there you stop with just single alkylation. And then how do you release the primary amine? You can use strongly negatively charged aqueous conditions, hydroxide and water. And this will do amide hydrolysis in a pretty fast way. I won't show you that mechanism, but it releases the nitrogen. And then the byproduct is this acid, this carboxylic or carboxylates, where you have two carboxylic acid groups on adjacent carbons. That part comes from this portion of the molecule. So you can see what you're doing under those conditions is probably hydroxide attacks a carbonyl carbon, you get a tetrahedral intermediate which kicks off a leaving group, and then the leaving group picks up a proton. You do that another time and the amine gets released. Okay? So that's, yes?
Is this an equilibrium?
No, that step is irreversible. Yeah. And so that's one way that you can make, starting with thalamide, which doesn't have any alkyl groups on it, a primary amine. And so the Gabriel amine synthesis is to make primary amines, and it's pretty effective. Let's talk about some other ways that we have synthesized amines in the past. This is a review. You have used reductive amination before. This was an exam 1 problem. Reductive amination is a 2-part series. First you do imine formation, and then you reduce the corresponding imine with sodium borohydride or a similar reagent. So as an example, you can take an aldehyde or a ketone. We'll show you an aldehyde, but it could be a ketone. You could take an amine. This could be just ammonia, NH3, or let's just do a primary amine. And usually in imine formation, you need some kind of acid to catalyze the reaction. This is sort of glossed over in your text. I'm going to include it here because I've actually done this reaction. You make the imine molecule, not this particular reaction, but a similar one. You make the imine molecule in the first step, and then in the second step, to the same pot actually, you add your reducing agent, and that will then add a hydride to the carbonyl carbon. The nitrogen picks up a proton from the solvent, and you can install one and only one new group onto the amine. The new bond you're basically making is this one. Okay? This is another way to make amines in a controlled way where you don't have to worry about the possibility for alkylation. Okay, any questions about that? Good. Well, I mean, no, it's bad. You should have questions. But it's fine if you don't. It didn't mean that it was good that you don't have questions. It's a neutral observation that you don't have any questions. Gosh. All right. So what I want to do now is, I didn't get the slide copied over, so I'm going to go find where it is previously. And we're going to tempt you because we're going to scroll right by the key to an exam. Chapter 22. Nope. Also not. Okay. So there's a reason I'm not writing all of this down. In the 1850s, there was a high school kid, or whatever they call high school in the UK, who was doing chemistry in his basement. And maybe he didn't have a basement, I don't know, I'm just envisioning. And he was trying to make an anti-malarial molecule called quinine. Because malaria is a huge problem. Tons and tons and tons of people die from malaria. And so in the 1850s, chemists were interested in anti-malarial molecules. He was intending to react aniline, which you've seen before, with these oxidizing conditions. So that's a 351 set of reaction conditions. That's called potassium dichromate. It'll turn carboxylic acids it'll turn alcohols, primary alcohols, into carboxylic acids. What Perkin didn't know and couldn't have known at the time is that his sample of aniline was contaminated with two molecules that are similar in structure but not identical. These are ortho and para-toluidines. They should be more or less basic than aniline. More, right? Because of the electron donating methyl groups. Anyway, his sample was contaminated with those methyl groups, which turned out to be important. He didn't make quinine, and turns out it could not have worked. What he was doing could not have worked. He ended up with a chunky black solid at the bottom of his flask. Now, depending on what lab you're in, it may be worth your time may be worth more than the flask costs. And when you have a tarry solid at the bottom of your flask, sometimes you just throw the flask away. Not in the regular trash, you have to, but Perkin perhaps was trying to save money, so he decided to rinse the flask out with ethanol. And when he did, the ethanol turned purple. And he immediately thought, that's interesting. Because at the time, there weren't a lot of cheap and easy ways to get purple liquids. And he envisioned using that purple liquid to dye textiles. In fact, previous to this point, do I have the figure? No. The way that you dyed textiles was to isolate, to go find various mollusks and shellfish from the Mediterranean, grind them up, and extract indigo dye. In fact, you can read in Acts chapter whatever it is about Lydia, a seller of purple who supported Paul and Silas in their missionary efforts. And probably the reason she could support them is because she was a fairly well-to-do small businesswoman who made money off of this dye. And up until that point, purple was the color of the super wealthy and the super important. That changed with William Perkin. So look at yourself, and if you were wearing purple today, you have this man to thank. Now, you're probably no longer using the molecule that Perkin used, but he opened up a factory to make this molecule in 1857, retired a wealthy man at the age of 36. The molecule that he actually made was a mixture of molecules, but it looked like that. Pretty complicated. It turns out if you wanted to, we could go through it, but we won't. Because it turns out that German chemists learned from this discovery how to make some other dye molecules that were cheaper and easier to make. Some of them are still in use today, but that's not the end of the story, because some of those dye molecules inspired the discovery of chemotherapy and the idea of targeted drugs for not only cancer, but for antimicrobial purposes. So I'm going to tell you that story next time, and we're going to learn how to make some of those dye molecules and antimicrobials. Okay. God bless you on the test. Good luck. You're going to need it.